but pretty soon I'll be thrown out of the home. That's for sure, uh, uh, because none of my weekends are free. In a way that every weekend there is something or the other. Saturday,
Okay.
Sunday, even starts on Friday night because Saturday
Yeah.
morning in India time, right?
Right.
And not only
Yes.
in
Yes.
India, it's all over the world. As a result,
Yeah. Yeah.
I'm sorry, I am actually saying no to a lot of things because I'll have to, keep my marriage. So,
Keep
uh,
your bonding.
yeah,
Okay.
yeah,
Yeah.
this is
Yeah.
my personal kind of, selfish motive because I love to stay at home. So that's why I'm saying no to people. Otherwise, it's crazy. I'm worried sometimes that, there should not be webinar fatigue because, it
Yes.
takes a toll on you looking at the screen for a long time. It is not
Right.
healthy.
Right.
So, also you get tired much faster and you cannot really keep your concentration that too long. At least for, my concentration span is not very large. As a result, after a few minutes, I kind of, tune off. So that should not happen while giving a talk, right?
Yeah. 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 You're right. You're right.
Right.
So
That's a
that's why I have started saying no to a lot of these things. I'm sorry. I know a lot of people are interested. And after some time, you run out of topics as well. What to talk about?
Yeah. 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 Yeah, and nowadays, like after the webinar, they
sorry.
are like many people are like recording it and putting it in the YouTube, and
In the
people
on
can
the
access.
YouTube, or that's already whatever you
Yeah,
wanted to say. Already you have said.
yeah, yeah,
Gautam, that's why we thought of coming up a event like this. Like, with all due respect to all the organizers, it has become like cricket in India. In every lane by lane, if you have a ball and bat, people start hitting. Like that, it was happening, and we should have proper focus. And at least we should know when you are organizing something, whether another event in the same area is there on that day or not. So those type of thing was not there. So we thought of like launching an event which will be really beneficial and impactful, especially for youngsters.
Yeah. So I think also one thing, if I may suggest, one thing might work well also, give opportunity instead of asking for people like us giving talk, ask, PhD students who are doing their PhDs, so that, that will be very useful for them. They will get feedback from people, how their research is going, and they can talk about the research, what they are doing, and then, people can give them feedback that will help in their research. So I think people should think in those terms as well. That will be very
Right,
beneficial.
right, right.
yes,
Yeah,
definitely.
that type of thought process is there as you suggested. So as I have already briefed on other day, so these L4 will involve talks, panel discussions from senior people and senior academicians and industry experts. As you suggested, that PhD talk at young student or young scientist colloquium, those are already there in our pipeline. Last week
Yes.
we
I
had
also suggested to Chinmoy, and many of you can join hands and help him organize that. One of the thing is that many students, I know, I can see 60 participants. Many of them are students currently doing PhDs, and they are interested in academic positions. Many
Yes,
of
right,
you have gone through that process of applying for an academic position, and that the student should hear from the people who are making those hiring decisions, like faculties at places like IITs and IISC and other places, that what do they look for when someone is applying for
yes,
PhD? What are the things, of course, there are a lot of different, bullet points in the sense, what is the academic credentials? How is the proposal?
right,
And all
yes,
those
yes,
details, if someone gives them an idea what to emphasize on when you are writing an academic position proposal, and what should they look into, so that,
right,
because people are not trained, if as a student, you are not really trained to write a proposal.
yeah,
And
yeah,
then, most often, my experience has been, it actually, the proposal doesn't make or break. I think it's time already, so I should not keep on going. Sorry.
oh, yeah, yeah, okay, okay.
Yeah, right. No, it's okay. Like what you suggested, yeah, we are in that as well. So there we'll have the senior people who, who really know what are the bullet points they look for, and also probably some youngsters who have experienced this kind of
Hmm.
stuff recently. So
Hmm.
we can have a mixed panel. So
Yes.
we'll have that pretty soon, maybe. Yeah.
Yeah.
So
Okay.
we should start now, Orijit and Sibada.
Okay, sir, we can start.
So is it like recording and YouTube live is already on?
Yes,
Yes.
sir. YouTube, it's going live on YouTube.
Okay,
It's already going. Okay.
okay. So Orijit, you can
Yeah,
take
we
care
can start.
the formal way to start maybe. Yeah.
Good evening and good morning to everyone. I am Arijit from the SSC ISRO. On behalf of IEEE MTTS Kerala chapter, welcome all of you in today's event. In order to continue with our activities in this pandemic scenario, we had launched our webinar series, which got excellent response from participants. And now this encouraged us to launch our new lecture series under the name L4, Learn from Leaders, Learn from Legends. The L4 series was auspiciously inaugurated on 17th of this month by Dr. Ana Abu Jale, MPTS President, in presence of other dignitaries, and we had our first talk on that very day by Dr. Nuno Carvalho. Today, we are extremely honored to have with us Dr. Goutam Chattopadhyay of JPL NASA as a speaker for our second lecture of this L4 series. He is going to talk on design and innovation of sensors, antennas, and systems. I heartily welcome Dr. Chattopadhyay and thank him on behalf of MPTS Kerala for accepting our invitation despite of his busy schedule. Thank you, sir. We also have with us Dr. Chinmoy Shaha, chair and founder of MPTS Kerala chapter, under whose leadership and continuous guidance have made these events possible. And I also welcome other dignitaries like Dr. Javed Siddiqui, Dr. Devdeep Sharkar, and others who are present today. And also, I can see a lot of participants. I also heartily welcome them for registering and being with us today. So today's talk will be followed by a Q&A session, and all participants are requested to put down their queries in the chat box, which will be taken up in the Q&A sessions respectively. All the participants are also requested to kindly keep themselves muted throughout the talk to avoid any noise or disturbances in course of the session. So with this, we'll start our today's event. In the beginning, I'd like to request Dr. Chinmay Shah to say a few words about our this L4 lecture series, and then kindly introduce the speaker. Thank you.
Thank you, Orijit. Very good evening and good morning to all the participants and our beloved speaker, Dr. Goutam Chattopadhyay, who is very close to our heart in all fronts because he was one of the people who influenced us and who motivated us to form this MTTS Kerala chapter. I still remember the day at IMAC 2018 where I was attending the conference as a speaker and I was invited for a chapter chair meeting there. I was not a chapter chair at that time because I was chairing the APS Kerala chapter. But Dr. Goutam Chattopadhyay, Professor Siddiqui, and Professor Cole invited me in the chapter chairs meeting there. And there I got the idea and some kind of advice to come up with this MTTS Kerala chapter, which was finally inaugurated after due process from the society and the local section in July 2019. In fact, we are really privileged to have Dr. Goutam Chattopadhyay during the inauguration of the MTTS Kala chapter, which was subsequently reported in IEEE Microwave magazine. And on the same day, we had technical talks by him and some of the other lead speakers across India. So, as our secretary, Mr. Rorijit briefed, that we started this webinar series in around April 2020 and post lockdown pandemic activities, and very soon these webinar initiatives have been propagated very nicely without any kind of loss like propagation in a perfect dielectric medium. But at the same time, we wanted to have some event which will be really meaningful and beneficial for the youngsters and some of the students who are trying to find their research problem. And this L4 initiative, Learn from Leaders and Learn from Legends, is basically and path towards that, because these senior people who have accomplished and who have really had a very long race in their academic as well as research and as well as IEEE leadership career, some advice, some twist, or some kind of impetus, or some kind of advice from them will be really useful and helpful for the youngsters in shaping their career. So with this initiative, we launched this L4, last week, which was inaugurated by President Dr. Ala, and also President-elect 2021 Dr. Henderson was there, along with Dr. Chattopadhyay, Professor Cole, Dr. Gupta, and others. So as you know, these kind of webinar activities is going to stay for some time, because this is the new normal. And probably, as you have seen, many of the premier conferences, including MTTS Society conference like IMS, and some APS conferences like APS 2020 and 5G conference, all these events has gone virtual. So similarly, our academic process, learning, even research for next few months is going to remain like this. So we have come up with this type of initiative, and I sincerely believe that this is going to be very, very useful for all of us. So I will not extend, because we want to hear from our L4 speaker today. Just to mention that this initiative will have other kind of variations also, because very soon we are going to come with focused panel discussion, speakers on different focus themes, which will be related to research, shaping your careers, how to write a meaningful proposal to different organizations, or how to make a good application for your CV positions, etc. So we have some future plans which will be revealed very soon in a weekly fashion. So with this, I want to conclude my talk, and let me take a couple of minutes or so to introduce our speaker, beloved Dr. Goutam Chattopadhyay. So I'll be just sharing my screen to show just a couple of slides or so. You see my slide, Sivada?
It's done. Plan screen is
It's looking, you can hear.
Okay, so just let me know when it is completely visible. So these learn from legends and learn from leaders initiative we started on 17th of this month, and these are the flyers. On the same day, after the just before the inauguration, we had a leadership talk by Professor Cole, followed by a technical talk on wireless power transfer by Nuno Carvalho, and this is the inauguration of L4 series, the virtual photo shoot, and this is going to appear in Microwave magazine, I believe so. We are in the process on that. We are really privileged to have many leaders and legends, including our beloved Goutam Chattopadhyay on that day. And the today's session is divided into two parts. Part one will be technical talk, and followed by the interaction. And in part two, we'll have not only the technical queries to be addressed by Dr. Goutam Chattopadhyay, we'll have some other kind of questions, other kind of interactions also from leadership aspect, as well as other queries which we have to him on behalf of all the audience. So this is the flyer of today. And as you know, Dr. Goutam Chattopadhyay doesn't require any introduction. He's a senior scientist from NASA Jet Propulsion Laboratory, fellow of IEEE, fellow of IIT. He's a visiting professor at California Institute of Technology. He's Bell Distinguished Chair Professor at Indian Institute of Science, Bangalore. He's an adjunct professor at Indian Institute of Technology, Kharagpur. He is also associated with Cochin University of Science and Technology as an erudite chair professor. So with this, I stop sharing, and I'll now read out his CV. So this is a formal introduction to Dr. Chattopadhyay. He is a senior scientist at NASA's Jet Propulsion Laboratory, California Institute of Technology, a visiting professor at Division of Physics, Mathematics, and Astronomy at the California Institute of Technology, Pasadena, USA, a Bell Distinguished Visiting Chair Professor at Indian Institute of Science, Bangalore, India, and adjunct professor at the Indian Institute of Technology, Kharagpur, India. He received PhD degree in electrical engineering from California Institute of Technology in 2000. He is a fellow of IEEE USA and IIT India and IEEE Distinguished Lecturer in Microwave Theory and Techniques Society. His research interest includes microwave, millimeter wave, and terahertz receivers, systems, and radars, and development of space instruments for the search of life beyond Earth. He has more than 350 publications in international journals and conferences and holds more than 20 patents. He also received more than 35 NASA Technical Achievement and New Technology Invention Award. He received the sorry IEEE Region 6 Engineer of the Year Award in 2018, Distinguished Alumni Award from IIST India in 2017. He was the recipient of the Best Journal Paper Award in 2020 and 2013 by IEEE Transaction on Terahertz Science and Technology, Best Paper Award for Antenna Design and Applications at the European Antennas and Propagation Conference, UCAP in 2017, and IET Professor SN International Award in 2014. So this is just a formal introduction to Dr. Goutam Chattopadhyay. One more thing I just want to add that beyond this, he is one of the best human being I have ever experienced in my life. So I request our beloved Dr. Goutam Chattopadhyay to start the proceedings. Thank you very much. Over to you, Dr. Chattopadhyay. Thank you very much.
Thank you so much, Inmay, for the introduction. And also, I want to thank everyone for taking your time off on if wherever you are. If you are in India on a Saturday evening, and if you are in out North America in a Saturday morning. So I really like interacting with young professionals, students. So that's why I agreed to this, and Chinmay asked me. I'm really grateful to all of you that I got this opportunity to talk. So I'm going to share my screen, and let's talk. Let's see. Can you see my screen?
Yeah, we see it already. Yes.
Okay, let me make it full screen. So hopefully that will work. So it's working. Full screen.
Yes.
Can you see?
Yes. Yeah.
Okay.
Yes.
So, that I have been requested to give talks, during the webinar, as Chinmay mentioned, that, we have now kind of during the pandemic, a lot of webinars have been organized, and many of you are giving a lot of talks and webinars, I know, and I am doing the same. So as a result, I was thinking that what do I talk in this forum? And one of the things I thought that it will be interesting to talk about is about the innovation part. That, okay, how innovation happens. Most of you who suppose you are a student, and then when you start doing your PhD, let's say, then you are given a problem, or you first search for a problem, and then you try to come up with a solution. In that process, actually, you'll have to innovate, because you'll have to come up with new ideas. So what is that process, at least from my perspective, how all these how you come up with new ideas? Because it is never that way that one morning you wake up and say, okay, let's innovate something. The innovation process is never that way. So most often innovation happens when you are confronted with a problem. We all know that currently we are under this COVID-19 situation, and if you think about it, that amount of a number of innovations that has been happening over the last several months is amazing, because we are in a global pandemic, and we are trying to come up with solutions how to address those. So whenever you are given a problem, that's what human mind actually starts thinking about it. And my thinking is that how it happens, the innovation happens, is that you work in a group. So innovation most often is not a single individual event, and that you interact with people, you talk about the problems that you are trying to solve, and then you come up with a solution. So what I'm going to do today, I thought that I will give you an example of a problem that we are currently solving. And there, most of you, if you actually distill it down, whatever research that you are doing in at least for in our area of our field, that you either build sensors, you build antennas, and you build systems. So basically in that, of course, there are parts, are components are also there, subsystems are there. At the end of the day, if you can actually categorize all those things in these three items, and that's why I thought I put together these three items, and let's see how that process works, and through that we maybe will be able to learn something. So that is the idea of this. So the title of my talk is Design and Innovation, Sensors, Antennas, and Systems. So before I start, I want to acknowledge my group members. So at JPL is a very big place. We have people from all different careers, all different fields. But we have a small group of about 24 people. We call Submillimeter Wave Advanced Technology. And if you look around all the faces, you'll see that they come from all different parts of the world. And that's what makes NASA successful, that we have people coming from all over the world. The diversity of thoughts, diversity of ideas, that helps. And I am so lucky actually to get this opportunity to interact all these highly talented individuals, and that's how we make new innovation, that's how we make progress, that's how we make new designs. And I am all the stuff that I'm going to show to you today is because of them, not because of me. I have been lucky to actually work with them, as I mentioned, that discussing with people, talking about the problem that you are trying to solve with others is the, I think, key to new design and innovation. So let's start with this. Let's look at the problem. When we innovate, how we innovate and when we innovate. So one of the things that, at NASA, what we do is we are trying to answer science questions. But suppose you are a graduate student, you are a PhD student just entering your PhD. Then you might say that, oh, we don't face this kind of problems, right? Our problems are slightly different. Yes, how the PhD program works in different parts of the world is slightly different. Like if we give the example of United States, here what happens is when you come as a PhD student, already a problem is defined for you, because you are coming, your professor, your advisor has already written a proposal, it has been funded, and that's why he wanted to hire a graduate student. So problem is already defined, and then you start thinking about how to solve that problem. But in other places, maybe you join in and then you start thinking about looking for a problem, because it takes time to find a problem that we are going to solve. So there is different kinds of way we progress. So here, what I'm going to talk about is we were given a problem is this. The science question is that the scientists believe that when Earth was created, there was no water, and comets brought water to Earth. So if you ask this question that, okay, did really comet brought water to Earth? How do you know? What kind of experiments that we can do to actually solve this problem? And then to do that experiment, what kind of instruments we need to build? So this is the broader, the situation that we are always faced. And then this example that I'm showing, that if you actually think about it, we have actually gone to comets and did some measurements, but the numbers, the actual results are all over the place. But we made only about 10 measurements showing that, trying to answer this question, that did water really come from comets, Earth's water? So this is the bigger problem that you are trying to solve. So I came up with an idea of solving this problem using a CubeSat instrument. So I made an acronym called Water Hunting Advanced Terahertz Spectrometer on ultra small platform. That's WhatsApp. You might say, why did I come up with WhatsApp? Because we are trying to answer the question, what's up with water? Did really water come from comets? Did water on Earth come from comets? So if you are trying to answer this question, how do you go about this answering? What kind of experiment you can do? If you think about it, the water that we drink every day is H216O. The oxygen has different isotopes. So most abundant water is with a 16th isotope of oxygen. But there are many other kinds of water. We can have water H217O, H218O, HDO, that is one hydrogen, one deuterium, and oxygen. So if you look at that each of those, water, they have a spectroscopic signature at different frequencies. So water has HDO has many spectroscopic signatures. One of the strong line is at 509 gigahertz. So H216O, that the water, most abundant water that we drink every day, is actually at 557 gigahertz as a very strong spectroscopic line. So if you can measure the abundances of different kinds of water and take a ratio and also make a ratio of the amount of deuterium and hydrogen in that water, that actually is unique to different comets and for our planet Earth. So if we can show and go to a comet and particular kinds of comet called Jupiter family comets and make the ratio measurements on those comets and find that they're the same as planet Earth, then we can confidently say that source must be the same. So that is the way to solve this problem. And then that you have to think about building instruments, right? So as I mentioned, that we wanted to use a CubeSat. CubeSats are very small satellites because if you want to go to a comet and do a measurement with a big mission, it costs billions of dollars. No, there was a mission called Rosetta mission. Then there we actually there was a lander even on the comet, Phillies lander, but it did not work very well. But we had an instrument on that from JPL. Where actually I was involved on that called MIRO, microwave instrument on Rosetta orbiter. There we tried to measure those, but they are very expensive. So can we make a satellite based receiver system or an instrument on a shoebox size satellite? So those are CubeSats. Lot of work is going on with CubeSats, and if you are a young faculty, if you are a student, then if you think about actually building instruments for CubeSat and then approach some of the space agencies like ISRO, NASA, ESA, JAXA, and others and fly your instrument. This is a great opportunity to actually make something tangible and then get some results out of it. There are many missions are planned in for future as well. So what is the key for building an instrument for this kind of missions that we are faced with? One of the things is miniaturization and integration. Why I say that? Because every kilogram of mass that you want to launch in space actually costs huge amount of money and challenges. So if you make your instrument really integrated and miniaturized, that helps you. What you are seeing on your screen, can you take a guess? It's actually the iPhone 5 entire system. If you open your smartphone, if you have not opened your smartphone, you should open your smartphone. That is a beautiful piece of instrument. So I did. I opened my wife's iPhone. That because it was water damaged, not that I was just playing with that. So if you look at that, when you open those smartphones, you will realize that what kind of engineering marvel has gone into that. What level of integration has happened. All these different chips. You can build one single chip, SoC even, system on a chip, but you have to put everything together, the connectors that you need to use. How do you place everything? How do you manage the thermal environment so that it doesn't get heat? Or sometimes, on your, smartphone, it gets hot when you are holding near your head. So how do you manage that? How the key aspects of it? You have to reduce power because for any mission, what kind of antennas you are going to use. Let's go through that one by one and then look at what is the process of innovation and how do you come up with solutions. So this is the block diagram of a, we are using as I said, because HDO line is 509 gigahertz, the H2 is 547, 552, and 556 gigahertz. So you have these lines you want to target, you want to detect them, you want to measure the amplitude of, the abundances of this. Anyone said anything? You can hear me, right?
Yes, sir, you're audible.
Yeah, you are
Okay.
audible.
So this is the block diagram. First, you come up with a block diagram, right? So this is what that should be an antenna, and then because it's a CubeSat sizes that we chose is called 6U. 6U stands for 30 centimeter by 20 centimeter by 10 centimeter. It is not a big volume because most of it is going to go for all other kinds of stuff. You have to have solar panels. You'll have to have a star tracker so that you know where you are. You need to have communication, all those stuff. So at the end of the day, for your instrument, you do not have much space. Mostly it's about 20 centimeter by 10 centimeter by 10 centimeter. So these are the challenges. So you come up with a block diagram, and you can see that I need an antenna. Since my face on the CubeSat is about 20 centimeter. So we decided to go with the 18 centimeter diameter aperture. Then we need to have a calibration system, so that you need to calibrate your receiver so that you know whatever you are measuring is a real, like way you calibrate your vector network analyzer. So that way you have to calibrate. This is in a way you can think about is as a vector network analyzer as well at this frequency, but not a big box. It is a very tiny small instrument. And then you need to have come up with a synthesizer. You need sensors, and also need the back end electronics. So these are all the requirements you have, but the constraints you have is that they have to low power. They'll have to be you have to have a very good antenna, in a low profile antenna, and you have to have low mass. So these are the challenges. So antennas. So I know many of you who are listening in work in antennas. And so we have been innovative in coming up with new kinds of antennas. This is shown, it's called Marco. Marco was a Mars CubeSat 1. That was a mission to Mars called InSight. On that, we had the first time we had two CubeSat for communication that went to another planet. And why it was needed? Because what happens is when the spacecraft goes to the Martian surface, there is no direct communication link with Earth. To begin with, it takes about 7 to 8 minutes for signal to reach at the speed of light from Mars to Earth because of the distance. On top of that, if there is no direct link, we don't know whether our spacecraft landed safely or not. So to avoid that, what was done as a technology demonstration, that we built two 6U CubeSats. Again, this is 30 centimeter by 20 centimeter by 10 centimeter, so very small in volume. It had antennas. One was UHF antenna to communicate with the spacecraft, and another was X-band antenna to direct communication to Earth. X-band antenna was a reflector antenna. My colleague, Nasser, many of you know, Nasser Chahat was involved. Manu, Emmanuel, he was also involved in the designing some of this. So a lot of people came together, and this is a deployable antenna, because to have a direct communication link with Earth from Mars, you will need large aperture, because you do not have enough power. So we came up with this idea of foldable antennas. This is a reflector array. So we are those problems we are faced with, and came up with a solution. But this is as I said, UHF and X-band. And also there was another thing that we did recently was called RainCube. RainCube is a radar on a CubeSat, but it had needed to have a large aperture at Ka band, so about 33 gigahertz. So this is a 50 centimeter deployable mesh antenna, parabolic dish kind of antenna that was needed because of the requirements of the mission. Then how do you come up with an antenna that fits in a very small volume and then deploys and works well? So that was the challenge. So here again, my colleagues, they came up with a very innovative solution. Again, when you are thinking, I keep mentioning one thing: teamwork, because you can be a very good antenna designer and come up with an antenna, but if you do not have mechanical help, how do you actually deploy this kind of antenna? How do you actually come up with all the mechanical architecture? So you'll have to talk to people who has expertise in all different areas. So one person is not enough. I always say, so that's a build team. Talk to your friends who has expertise in other areas. Go and talk to them. They might actually give you ideas, innovative ideas that you can actually run with it. So always think about that. So I'll show you a short video how many of you might have seen before, that how this antenna is deployed. This is in the lab. Once you release a pin, then this starts happening. This spring loaded, it starts opening it up, and this is the main reflector. This deploys, and then there is a sub reflector, because what you see here is actually a horn. This is multi flare angle horn in K band, and there is a sub reflector, and everything has to work well. Otherwise, as you know, at Ka band, if the position of the subreflector is not correct, you are not going to get the directivity and the efficiency that you are looking for. So again, why I'm showing all this, though this is not related to 500 gigahertz system, but we are faced with challenges and then we come up with new solutions, because that's when you start thinking, how do you solve this problem? How do you fit in a 50 centimeter reflector antenna in a 10 centimeter volume, and then when it deploys, it works well? So this was the challenge. So then we actually started thinking about a very low profile antenna. As I mentioned, for the CubeSat that we are trying to do, we cannot have, we cannot really make this kind of antenna at 500 gigahertz, which will deploy and work well, because if you look at the surface accuracy needed, we need about 15 micron surface RMS or even better. And then, so there's a lot of challenges. So we'll have to come up with a different kind of architecture. So, I have been working on some Metasurface antennas. So we thought, okay, let's look into this. Can we make something in metal that can go on the sidewall of a spacecraft? That becomes the antenna. So we came up with something called a fakir bed antenna. Fakir bed antennas, I call it, fakir is the term used in India in Sanskrit. It means saints, and they sleep on bed of nails. And if you look at these structures, these actually are nails, bed of nails. That's why I call it fakir bed antenna. So what it is, this is actually a metasurface antenna, all metal structure. So what you see at the center is a circular waveguide, and you have to circular waveguide. The dominant mode is T11, but what you need to generate is a surface wave, TM01 wave mode. So from a circular waveguide, you can generate the TM01, and when that surface wave is generated, it will propagate on that surface. However, if you can modulate the surface wave as it is propagating, you'll be able to get good radiation. And this is all metal. So entire structure is metal. So, in space, all metal has a lot of advantages compared to dielectrics, because dielectrics can get charged up in space because all these high energy particles are there. So all metal structure is important. This is a 300 gigahertz antenna that we developed. And you can see the height of these pins are about 115 micron. Thickness of your hair is 50 micron to 200 micron. So, people who are young, the 200 micron, people like me who are getting old, our hair gets thinner. So we get maybe 50 micron. So there, So not, it's just like a hair, the thickness, entire antenna is so thin. So you won't even realize that it's actually there's an antenna. So that there is circular waveguide, and behind that is your system. So if you, this kind of antenna is really interesting. So we came up with that and we did measurements and it works really well. So we fabricated this antenna using silicon micromachining. So you take a piece of silicon and actually make these structures. I have a colleague, great colleague, Cecile. She is expert in doing DRI techniques, and she fabricated these, and we metallized these antenna and tested it worked well. So we have now, you see, we've solved one of the problems of the antenna side, but that is not enough. Of course, how do we, there are a lot of other challenges. How do we make a 18 centimeter aperture with that? Because this antenna that we made is a small one, about 5 centimeter aperture. Then you'll have to tile them together. How do fabrication in your clean room when you are fabricating? Then making large wafers is not very easy. So there are challenges. So we still are thinking that, okay, we have to come up with maybe some other easier way to fabricate antenna. So we came up with two different ideas. One is a lens-based, very low profile antenna using a leaky wave feed. So what happens is that if you have a leaky wave feed, and then you can generate the feed pattern, not a Gaussian feed pattern, but more of a top hat radiation pattern, then you can illuminate a very thin lens at the top and then come up with a very good antenna. So we did design this antenna, and one of my colleague again, Maria Alonso, she was a postdoc with me, and then she joined JPL. Now she's a faculty at TU Delft. We worked together and then came up with the antenna we fabricated, and it actually worked very well. You can see here, this is an antenna working at 500 gigahertz, and this is 18 centimeter in diameter, and it has a leaky wave feed. The thickness of the antenna is only 7 centimeter. So this is very low profile that can easily fit in a CubeSat environment. So that was the idea, and we get good performance from these. These are actually measured performance of this antenna. And then we also thought, okay, we should also look at, because when you are outer space, if you are exposing a very thin silicon, there are a lot of challenges as well. So you should survive the vibration and all. So we thought that, okay, we should have as a backup, we should have another antenna design, low profile. This is a low profile reflector antenna, very low profile. You can see even the less than 7 centimeter. As you know, if you put a reflector antenna with a subreflector, Cassegrain system, then your subreflector generally is kind of far off. You can put a horn at the hole that is here, and then this is the subreflector at the center that you see. But we had to put the subreflector very close to this so that you make it a low profile antenna. And we actually fabricated, this is a fabricated antenna, and it works really well. So if you saw my first slide, the cartoon that you saw actually showing these antenna that we have. So we have settled down, we have a lot of options now. See, we had a challenge of making low profile antenna at this frequency. We came up with different solutions, talking to different people, and 3 different kinds of antenna we developed, and then we can use any one of those. So that is the advantage. Next thing that you'll have to think about it is that, as I mentioned, power is a big problem for this kind of instruments, because whenever you are trying to generate a signal at terahertz frequencies, you need huge amount of DC power, but we don't have for our CubeSats instrument. So one of the things that we started looking to SoCs, because it's that iPhone technology. If your smartphone, you use SoCs, right? System on a chip. It is a CMOS based system. And then I had we have a great engineer with us, my colleague, Adrian Tang. He graduated from UCLA with Frank Chang's group. And then we started devoting our time developing CMOS based synthesizer that works at W band at 90 gigahertz. So this is CMOS based circuits at 90 gigahertz, because if you buy a synthesizer at if you look at your signal generator, if you're actually looking at that, then it is a huge box, and it needs a lot of power, but we cannot afford to do that. So we came up with this SOC-based synthesizer, entire synthesizer, which draws less than 200 milliwatt of power at W band. So that is amazing. So we actually did that, and it works really well. You can see here the phase noise. This is a measured phase noise of this synthesizer working at W band. This is at 90 gigahertz, at 90 dBc per hertz at 1 megahertz offset. That meets our requirement. And then also we need backend spectrometer, because when you get the signal, you'll have to actually, spectrometer is a spectrum analyzer. So we'll have to build an entire spectrum analyzer working at 3 to 6 gigahertz bandwidth, but draws about less than 2 watts of power. You know how much power your spectrum analyzer draws, the one that you have on the desktop, is huge. But we actually solved that problem. Again, we came up with the solution of developing a 3 gigahertz bandwidth spectrum analyzer, spectrometer with 4,000 channels. That means that each signal is about 750 megahertz wide. So we solved that, and now you can see that if you buy a commercial synthesizer that can go on your spacecraft, draw 6 watts of power, we are now drawing only 200 milliwatt. And these commercial spectrometer that you can buy that draws about 10 watts of power, now we are drawing 2 watts of power. So we came up with this solution to solve this problem. And then there are a few other things you need. This is the instrument that we put together, the first generation of instrument. This is the entire spectrometer, but we need to have a calibration, because as I said, that without calibration you won't know what you're measuring. So how do you calibrate such a system? There is something called flip mirror based technique in space, because what you can do is your system can look in the cold sky. Our sky is cold, 3 Kelvin. So if you can actually look, your instrument can look at two different temperatures, that is two different loads. One is very cold, one is hot. Then you can, from that, you can calculate the power that is going in, so that you can know what is the gain of your system. And from there, you can calibrate your system. One of the way that is done traditionally is using, you can see here on the left, there's a flip mirror. There's a motor that flips the mirror, because this is a quasi-optical system. The beam that comes out of your horn hits the mirror, and the mirror can actually reflect that to your load. This is actually room temperature load. Or if you move it out, then it goes straight to the sky. That's what you are trying to observe. So, but it again, this motors needs power, and this is a mechanical system. So there is a single point failure. If it motor is stuck, then our system is not going to work. So to solve that problem, we came up with a MEMS switch at terahertz frequencies. This is for the first time anyone actually built a low loss switch that can replace this flip mirror technique. So I had again another postdoc who joined in as Theodore Reck, and all of us worked together and came up with a MEMS-based switch. What you see here on this is two are waveguides. So how you all know about waveguides? In a waveguide, if you change the A dimension of your waveguide, you change the cutoff frequency, right? So waveguide is a high-pass filter. So which means that if you're above the cutoff frequency, you have transmission, but below the cutoff frequency, it's actually stopping everything. So it can act as a switch. If you have two waveguides, and if you have very thin aperture, you can see the kind of septum. If you, with the MEMS structure, you can move the septum in and out of your waveguide, changing the A dimension. Then what happens that one of the waveguide you can make it under cutoff, other one is open, and if it moves away, then the other one becomes open, and this one becomes under cutoff. So in that way, you can make a very good switch that can look either in the sky or to your load. So we can replace the mechanical system altogether. So we actually build this. We have designed it, fabricated it, and it works. I'll show you. On a video, you'll be able to see that how the two septums moving in and out of two waveguides. So opening one and closing the other, and the vice versa. So hopefully you'll be able to see this. You can see here, once we actuate it, and you can see here, it's moving. This is at the center, all those orange, those two are waveguide vertically looking down, and you are actually changing, the cutoff frequency of those waveguides. And this is a very low loss system that we built, so that it worked really well. So now we are actually using these in our system. So we solve the problem for this, calibration as well. So, but if you're looking at, if you have what we do in this with the spacecraft is, as I mentioned, one of the temperature that you can look at is the load that will be, let's say, room temperature, but we need another temperature, and that is looking at the cold sky. But if you have a CubeSat, you do not want to turn your entire CubeSat to look at the cold sky. So what we did is actually came up with a load that is, programmable uh, temperature, in the sense that you can change the load temperature with over over a long range of temperatures. Again, it has to work in a waveguide system at 500 gigahertz. So we did is we came up with this idea of there is a lot of feedback system. We heat it up and get different temperatures. It has to be very accurate. We read it out, and you can see here, this is the design that we did of the load, and these are all waveguide structures at 500 gigahertz, and it is working really well. You can see the match is very good. We have PID controller. We actually change that, go about 600 Kelvin, so we can change from 300 Kelvin to 600 Kelvin. So, and in very accurate and controlled way, so that you know the temperature very well. So now we have the antennas done. We have the system, we Schottky diode system that we have been using as sensors. We have low power synthesizer. We have low power back end spectrometer. We have a MEMS based switch and a calibration load. Now we are ready. If you put now everything together, what you get is your system. This is the entire 500 to 600 gigahertz spectrometer instrument that actually can do a lot of things. A lot of people are interested in, for this kind of instrument, for space, for planetary exploration. You can see the total mass of this instrument now is 2 kilograms, and the total power required for this instrument is less than 5 watts. So if you look back where we started, if you actually, before we started doing all this, the total mass for an instrument like this is to be at least 20 kilograms or more. And the power needed to operate this kind of instrument about 80 watts or more. So that is beyond a CubeSat system. You cannot put a 20 kilograms mass and 80 watts power requirement in a CubeSat-based system. It's not doable. But now that we have made all this innovation and these new designs, now the mass and power in a range, and without really sacrificing the performance of this instrument, then we can fly it now. It's ready. So we actually, to demonstrate that everything works, we are putting in a balloon we'll fly it in the next year. Actually, we were supposed to fly this year, but because of pandemic, we are not able to do that. So it's ready. So this is we actually put together a balloon-borne instrument that will fly to test. So that was, what I was trying to tell you all from the beginning, is that how the innovation happens, that you are faced with a challenge, you are faced with a problem that we'll have to solve this, and then you start thinking about how do we solve these so that we can get the result that we desire. And then you have to put all the brain powers together, come up with a solution, try it out. You'll fail, all this stuff that I have shown. I'm telling you a success story. What I'm not telling you is a lot of things that did not work, that we have to really scratch our head. So if you design something and it works, you go and you design something, you fabricate it and go to the lab and test it, and it works great in the first try, you should be doubtful. You should be thinking, did I do something wrong? Because, most often, our world is such that it doesn't work in the first try. So, there are a lot of heartbreaks, there are a lot of, heartaches. So it happens. But at the end, if you keep trying, in Hindi, they say, lage raho munna bhai. So if you keep trying, then you'll be able to, come up with a solution. So I will end with something else, another innovation that was done recently. Many of you know about it. And 2 slides, then I'll open it up for questions, because I know you have a lot of questions. So I will talk about Mars helicopter. I'll end with this. Again, Mars helicopter was, what was the need of Mars helicopter? What was the need, and how do how did we come up with this solution? So you know that we are sending a rover to Mars. What happens to the rover is that rover goes there and it lands, and then it is already pre-programmed. This is the most expensive autonomous car, self-driving car that we can build. So that is the rover, and it has all this obstacle avoidance and everything, but it's a limited range of where you can go and do experiments. So we thought that if we have a helicopter on at the rover that we can take off, and it has all these kind of sensors, they could go around, take pictures and get other data and send the data back to the rover, and then the rover will go there and do experiments. That will be great. But there is a lot of problems. If you make a small helicopter on Earth, the blade that goes around, the rotator blade rotates about 400 to 600 RPM. But Mars atmosphere is much lighter. So you need to have much higher rotating speed, about 2,600 to 3,000 RPM. That is huge. So that you have to come up with new materials. You'll have to come up with, so that you have the lift that is needed. And total mass has to be very low. But again, it has to be power. You need power for a helicopter to go at, the rotator to rotate at 3,000 RPM, and go on top of that. You need to have sensors, you need to have communication system to send it back. So there are lots of challenges. And again, it turns out that when the mechanical engineers did the design of the blades, they used a material which is very much like metal, and you need to have antennas that is communicating. As antenna engineers, many of you know that if there is a metal obstruction in front of your antenna, all your carefully designed radiation patterns goes bust. So we'll have to solve a lot of problems, but we did. We actually, attacked each and every one of them, came up with innovative solutions. And then this is the Ingenuity helicopter that got ready, and it has just before, when it was actually integrated with the Perseverance rover. It is on its way right now to Mars. It will land, the rover will land on Mars in February 2021. And then let's hope that the helicopter gets an opportunity to fly on Mars. That will be for the first time helicopter flying on another planet. So that is really cool. So that's why, when you do innovate, when you come up with new designs, you actually feel really great. So that is the best feeling in this world. So with that, I'll end. And so I will stop sharing my screen. Thank you very much.
Thank you. Thank you very much, Gautam, for your excellent talk. And always it has been so illuminating, and you covered quite a aspect, a 360-degree view of space research in general, but you also talked about two specific cases of innovation. So now we come to the second part of this L4 series, where we have some technical queries in the chat box. Also, some of our office bearers and some of our friends want to interact with Dr. Goutam Chattopadhyay, because the whole idea of this L4 is to hear from the speakers, not only on the technical fronts as well as other fronts also. So before I do that, I take the questions from the chat box, and I request some of you to speak. I'll just once again go to sharing the screen and go to the second part of this talk. So thank you very much to all of you for your patient learning and hearing. So here we start the second part. Here the legend. So As many of you know, the journey of Dr. Goutam Chattopadhyay from a village of Kolkata in Hooghly district, that from to NASA, from there to NASA has been a phenomenal journey. He has achieved so many laurels and so many achievements in all fronts, starting from academic fronts to IEEE fellow, as well as many best paper awards, many recognition in IEEE journals and forum. So here I, give you the opportunity to know from about his journey, and you can feel free to ask him also very soon. These are glimpses of the journey of our speaker, Dr. Chattopadhyay. He did his early education in a school from Navogram Vidyapit, West Bengal, India. Then Bachelor of Engineering from IIST Shibpur. Then ME from University of Virginia. He is from Caltech. And as I have already mentioned, you can see from his profile, he has many publications and patents in his credit, and these are some of the awards editions he has received. IEEE Regents Engineer of the Year Award in 2018, Distinguished Alumni Award from Indian Institute of Engineering, Science and Technology in 2017, Best Journal Paper Award in various forums, and in UCAP as well, and IET Professor Esen Mitro Memorial Award in 2014. So we contacted Dr. Chattopadhyay to say something about his early career, because being a very close friend of him, and already blessed with on various fronts. So we know some of his early days fights and how he have grown up from a small village, and little bit of of different fronts in his family. But he has been, the main point is he has always been grounded. He mentions this particular thing during his talk also. Even if he works for the space antennas, but he has been always grounded, and he is always very supportive. And he, that's why you can see some of his photos, like with his brother, and then you can see with a photograph with his school teacher in front of the California Institute of Technology. So I'll be requesting Dr. Goutam Chattopadhyay to say something about your early career, about your journey from Navogram to NASA, of course, through various paths and various milestones. Over to you, Gautam.
Oh, okay. Thank you, Chinmoy. Okay, so I grew up like many of you in a very small village outskirts of Kolkata, and then for us, I have only one picture as a kid. This one myself and my brother, because we didn't have a camera, of course. So someone took this picture, and we found it high, in one of the trunk somewhere at home. So that's what I took this picture. I took scanned it, and so again, I don't want to talk really more about, and I don't want to highlight our poverty and all, but that is also part of us, that many of us go through the similar kind of situation. So in a way, so I tell this story so that you know that if you work hard and if you have a goal in your life, so there are a lot of challenges, but still there is a way to overcome those challenges. So in my personal life, we did that when I'll tell you a story. When we were in third grade, actually my brother is 1 year younger to me. His name is Buddhadev Chattopadhyay. We actually studied in the same class. So he was not that I failed in one grade, that he was 1 year ahead in school. And then we were in third grade, and in our school that I used to go in our locality, it was not completely free. We had very minimum, some a couple of rupees per month fees. But my parents struggled to pay that fee, and one we were writing our exam in third grade. And in India, at least at that time, I don't know if the situation has changed, people really didn't care about how the kids psychology will work. So since our fees were not paid, we were asked we called in front of everyone and thrown out of a exam, third grade exam, and we were sent back home. So again, how it impacts the psychology of a small kid is people don't really think. And then again, my mom somehow was able to convince the school authority to allow us to sit in the exam, and we could not write that exam fully, the one that we were thrown out of. So again, but okay, we did okay. So, but one of the things that I want to talk about here is that that did not really make me bitter. So not me, not even me, not my brother, because that's what we face in our life. We will face a lot of challenges, and many times things won't be fair to us. That we see all the time. Yes, we'll have to fight to make those changes so that these things are fair. But at the same time, we'll also have to make us resilient to stand up back and not feel bitter about it. So that's what I want to tell you about that. So I went to Bengal Engineering College, the second oldest engineering college in India, and then from there I went to TIFR, Tata Institute of Fundamental Research. You can see of the picture the Govind Swarup, Professor Swarup, who recently passed away. So I got this opportunity to work with him, and then came to US and did my masters in Virginia. And then I had this, bee in my bonnet to, go apply to Caltech. I was very fascinated about Caltech, MIT, and all. So I applied there and got this opportunity to work there. And I came to Caltech, and then when I came here, I though was in the electrical engineering, but my advisor was in physics. And every year during winter time, next 3 doors next to my office is to be Stephen Hawking, is to sit there. So I used to talk to him, and a lot of famous physics professors. So I had a lot of exposure to physics, and that way really helped me in my career understanding, because you have to actually understand if you are working in space in industry or space organization, its science aspects are very, very important, that you'll have to understand what science you are doing. So that helped me. So that, and then after I was finishing my PhD, I got a call from NASA to ask me to join there. And I was, of course, very, very happy, jumping up and down, because that was my dream place, and I am loving every bit of it and really enjoyed this. I always feel I'm a student, because there's so many things to learn. And I say one thing that I really mean it when I say that more you learn, more I realize that how less I know. So that is one of the thing, realization that comes to you. And with that has been my journey. It has been a, sometimes I feel I'm still dreaming as a kid. But I'm living my dream, and I'm so lucky and fortunate to get to work with really great people. Because if you want to be successful in your life, my advice to you is that surround yourself with smart people, and who are smarter than you are. That's what I have done. I am right now amongst people who are all of you are smarter than I am, and that makes me very happy. So with that, I am ready to take questions on technical questions. But again, I want to say that I cannot really go and read all the questions, so someone else will read it for me. So if your question is not answered, not that I am ignoring you, is not because they are the one who are going to ask those questions.
Yeah. I'll do the moderation for the technical questions that we see on the chat box. But for that, thank you very much once again for wonderfully talking about your early journeys. And we know these are some examples because the way you have compared the different situations, and you have come up to this particular position, and you have enlightened the entire academic as well as research community, especially in the frontiers of space research, is phenomenal. So, hearing that journey, especially for some of the people who are not aware of, is probably very, uh, so here we have technical questions in the chat box. So one question is, it's not a technical question though, but I think it's a very important one. So what is the way to get some kind of internship opportunity in NASA? So that
So,
is, yeah.
okay, before I answer that question, Chinmoy works at in a part of ISRO. So you should look into your, if you are from India, you should first look at internship opportunities in ISRO. And so that is very important. Then you should, of course, look for NASA has a lot of internship opportunities for students. And so you should go to nasa.gov website, and there are some restrictions, because restriction is that we can take only about total all across NASA centers. We can take 100 international students per year, only 100, because that is posed by State Department. So the limited number of openings. So every year the internship portal opens up sometimes in January. I know that a lot of people, first thing when they connect with me on LinkedIn or somewhere else, first thing they said, give me an internship. So I cannot give you an internship, because that is the way the NASA actually handles is very different. Individuals, we cannot really go and tell you, oh yeah, come over for internship. We cannot do that, because we have to be fair to everyone. People are applying from all over the world. And so we'll have to be fair. We'll have to have a fair process. So that's why there is a central, system. You apply there, and through evaluation, that's how you can come. So go to nasa.gov and look for internship opportunities for students. Again, international students are allowed for internship, but there are a limited number of openings.
Yeah, yeah. Sorry. Thank you very much, Gautam. During talk, you are talking about the international set of people in NASA as well as in your research group. You have a spectrum of researchers, PhD and postdoc from different countries. So you said that is one of the strength of NASA as well as your research group. So can you also talk on, as a follow-up of this question, I would request you to talk on the process of getting a PhD position or a postdoctoral position in your group, as well as in general the JPL Caltech, you know,
So
from
again,
that.
so for postdocs, NASA, we actually sometimes have co-advised students for PhD, but we cannot take direct PhD students. What we do is we actually have postdocs. NASA has a very good postdoctoral program called NPP, NASA Postdoctoral Program. So you can do a Google search on NPP, NASA NPP, then you will see. So what you will see there is that people who are advisors, as postdoc advisors, we put requirements. So you can go to scan through that. That is for all across NASA, and then which matches your interest. It is very important. I see someone is working in completely different area, but says, "Oh, I want to work with you." uh, I cannot really take you, because these are very specific requirement that you'll have to put on the website. And if your interest, if your expertise matches those, only then we'll be able to take you. So go through that and see which one matches, and then you can apply. Then you can contact the person who is working in this area. Sometimes we already have few postdocs, then we cannot take in any more, because there are a limited number of people one can take, because these are these are paid. NASA pays from their own fund. There's a separate fund for that. I want to pay from my own research funds. So and these are well paid. These postdoctoral programs are very well paid programs. So you should look into that. So that's why they make selection. I don't have any hand. Even if I want a postdoc, I don't have any hand in selection, because selection is done through the committee. They go through all applicants, then they rank them, and accordingly the amount of funds they have, then they decide. So you can apply. You can talk to the people who have put in the advertisement, but again, just be aware that decision is not in those individuals' hand.
Right. Thank you very much. There are quite a few questions in the chat box, but I won't go, one by one, because few of interlinked or connected questions. So I'll those questions, on my own in a different perspective, so that more or less all the things will be covered. There is a focus question from a PhD scholar. So first is appreciation about your talk, and then the next point is how can we exactly confirm the origin of water in Earth through WhatsApp? So this is the first part of the question.
So, okay, the question, as I said, that as we know through our measurements, we know very accurately what is the ratio of different kinds of abundances, a ratio of different kind of water, and what is the ratio of D over H. That we can do measurement here, because these measurements are extremely high quality measurement that we do, because these are very high resolution spectrometers. Their sensitivities are parts per trillion. So if there is even one part of water available in 1 trillion of other molecules, in gas, you can still detect them because they're very highly sensitive measurement. So these ratios, once you know on Earth, and if you go to another comet and you do the measurement and you find the ratios are same, so that's the link. That link is that the sources has to be same. Otherwise, you do not get the same ratios. So that's how we can actually be confident that, again, your confidence comes from the capability of your instrument, that what the instrument is capable of, what is the sensitivity of your instrument, how well you are measuring, how your measurement is not corrupted by other measurement. So yes, it is not a very simple process. It's not that just take the data and you are done. It has to go through lot of looking very carefully before we actually make any of such announcements. We go through, like all of you, all of you actually check, double check, same way we do that same thing.
Yeah, in fact, very nicely addressed, and in fact, you have already addressed the second part of the question. But just I would, read it out. Won't there be interference with the heat generated by active components, since the frequency we look up to is 500 gigahertz? So this is connected with the previous question.
Yeah, so there's a very good question. Yes, heat is an issue. However, our active component, this is a passive instrument. I just want to make sure first, this is a passive instrument, not a radar. We are not transmitting anything. We are actually detecting it. The generate power that we generate is to do the heterodyning, because the local oscillator of our system, heterodyning gives us very high frequency resolution. So that's why, because we need to isolate the line with a very high spectral resolution, like your spectrum analyzer. When you change your resolution bandwidth, and averaging, you do that by changing your video bandwidth, right? So it's very similar to that. So what is the resolution bandwidth of your system? And that's how we can isolate the line, and we can measure the line very accurately. In terms of corruption, yes, if you generate too much of heat and your sensor that you are detecting, it gets too hot, then your noise performance of the sensor goes down, right? So you cannot really, then your sensitivity goes down. So we'll have to make sure that you do a good thermal design. But again, we are doing spectral measurement here. It is not a radiometric measurement, it's a spectral measurement. So that's slightly different on that. But you can actually still act, depending on what sensitivity you are getting at the given temperature of your detector, you'll be able to know, what is the signal strength that you are receiving.
Yeah. Very nicely addressed, Gautam. Just to connect with this particular question, I would rather request you to address a few issues related to, the difference between the conventional academic research and space research. Whenever we talk about any component which is for space or space qualified, be it antenna or be it circuit or any system for payload applications or whatever, we have to go for a huge temperature testing. The system has to work from several of 100 minus of 100 degrees centigrade to plus few hundred degrees centigrade, then vibration test and etc. So in general, can you please talk about the extra focus or extra care that is needed for complying the and stamp that particular component is compatible for space application?
Yes. Again, very important question. Wow. So there's some feedback. So anyway, so the answer to that is that, okay, So there are a couple of things that very important for space is it has to go through vibration. So whatever you design,
Right.
we do the components, we do the subsystem, system level, and the system level. We go through lot of tests. Like all space agencies, they go through called thermal vac, in the sense that you'll have to do in a vacuum chamber, because space is a vacuum. So you'll have to, in a vacuum chamber, you'll have to go through the thermal cycling, that can it withstand the temperature, and can it withstand the thermal cycling that it goes through. Some on the surface of Mars, temperatures, it varies quite a bit. And even if you are going through space,
Right.
temperature gets very cold and then it warm. So does it survive those? So thermal vac is one thing that you have to test. You have to radiation environment, you have to test, because outer space, the solar wind creates all these high energy particles. They're constantly hitting your detectors. Can they survive? What kind of radiation level your system can survive? And if what kind of shielding you need to do for that? So that, of course, you'll have to pay attention to that. And quality assurance, you'll have to do, does it survive the launch? Because it will go through a lot of vibrations. So yes, we do go through all these different kind of testing. That's why it takes time. That's why it's very expensive business, because you'll have to make it just not that it works in the lab and you are done. That is, it does not work that way. Another thing I just want to mention, that another thing that we very important that we actually pay attention to is called planetary protection. Because if you are trying to actually detect life on other places, you should not carry life from Earth, right? So we have to make sure we scrub our instrument, scrub our spacecraft very well, so that we are not carrying light from here and detecting there. So this is a very, very important aspect of our space missions.
Exactly. Thank you very much. Probably one takeaway from this particular part of the interaction is, especially for the youngsters, when you're them, you should also see the different constraints that the space research will have on your system. So making an open-ended research is good, but when the research is linked to certain applications, be it industry applications or specific space applications, you will have more constraint on your design, and thereby in long run probably you will be benefited, because your research will be more close to the system design or for certain applications. So I so one query, a quick query rather, I would say, regarding the future of metasurface antenna.
Yeah, future. This is a very good question, right? So you are asking me to. This is not a simple question, because I don't have the silver bullet to tell you what the future is. But metasurfaces are looking really good in many different applications in terms of antennas. That we can see that it has advantages, but it has disadvantages also. If you look at the metasurface designs, one of the problematic area for metasurface is the bandwidth, because if you see that they're primarily narrowband, and the second issue is about their efficiency. There is recently there was a paper by Stefano Macchi, he's my collaborator, Stefano Macchi from Italy, that they have shown theoretically we can get about 85% efficiency for this kind of antenna. However, practically we still have not reached there, so that we have a long way to go. So those are the areas. Of course, whenever you are trying to doing something for us, we need something that needs to work. So it is not about just the meta surface. We'll have to see that what are the pros and cons of this. So there are a lot of pros, as I talked to about. It can be low profile. It's a very different kind of antenna, but there are some cons as well. So we'll have to be cognizant about it.
Thank you very much, Goutam. So one more query related to the space research is, how can you be sure that the comet under observation has the same water ratio as the comet that brought water to Earth?
So exactly. So because because most of the comet that we believe that we see different kinds of comets. So one kind of comet is called Jupiter family comet, because which comets actually coming out and then through the Jupiter, and it actually gathers water, and then they flew to near close to Earth. So they call the Jupiter family comet. The one of the plots that I showed at the beginning of what I talked about WhatsApp, there, you had seen all different kinds of comet, and some chondrites and different kind of comet. So we are particularly looking at Jupiter family comets because we believe so far the evidence, as some of the measurement that we have done, we are finding those comets has very similar ratio that I was talking about on in and to our Earth's water. So that's why we kind of believe that those are the comet that brought water to Earth.
Right. There is a question by Dr. S. Raghavan. He's a senior professor and recently retired from NIT Trichy. So I would request, if you are there, kindly you can ask the question directly. Professor Raghavan, you may unmute and please ask
Oh,
the question.
thank you, sir. I would like to know how many percentage of NASA scientists.
Okay, so good question. Actually, there are a lot of Indians in NASA. That is for sure. I won't be able to tell you exact percentage. Because I'll have to take a guess in that case. But one thing I can tell you, there are a lot of Indian people in NASA. That's for sure.
Right. Right.
Thank you, thank you,
So,
sir.
yeah. So, Professor Raghavan, if you have any other comment in general or any other generic question you can ask.
No, no. Today's talk has
Okay.
inspired many persons. That's all I want to comment. Now, people are imagining after reaching NASA, they will work with the new, really a legend. Thanks.
Thank
Thank you.
you.
Thank you.
Thank you very much. So
Thank
before
you,
we
sir.
go to the before we go to the few more queries, can we have a group photo? May I request all of you to turn on your video or camera? Our volunteer will take a screenshot.
Yeah, now I can see some of the faces. Yes, I recognize many of the faces now.
Sir, it's over. Like,
It's done. Okay.
yes, sir.
Thank you. Thank you. We have Professor Siddiqui over here. He connected very early morning from Kingston, Ontario. So I would request Professor Siddiqui to say something on this occasion. Yeah.
Yeah, thank you very much, Chinmay, and thank you very much, Goutam. I was waiting for this lecture because I said I heard numerous lectures that was delivered by you on life beyond Earth and all these parameters. But this lecture, the topics that you discussed about regarding in the motivating researchers, that's the need of the hour. Like showing them a roadmap, guiding them the roadmap, and as you said, like we are looking at NASA, but why not ISRO? There are opportunities of ISRO, and ISRO is doing well. So if we look at home and try to build some indigenous systems, and of course you are there, there's a guidance light, so like we might benefit more, and we can invite postdocs, and Chinmoy and his team, IIS team, they are doing well as a new institute. So like ISRO can attract students from all over the world, and definitely would compete with NASA. So that's what I'm hoping for, and I hope the students have been illuminated by this lecture. And it was great to hear to you, and thank you so much. Thank you very much.
Thank you very much, Chad. So on this point, I would just like to highlight that we have a very strong relation with JPL and Caltech also. We have our own nanosatellite program, and we have a scheme through which some of our toppers go for higher education in Caltech from Department of Avionics, Department of Aerospace, and Department of Earth and Space Science. Every year, the topper goes to Caltech for MS, and incidentally, they are the fast rankers in Caltech every year almost. Like, and in general, in our program, through that nanosatellite program, we take students who write to our group. Dr. Priyodarshanam is there because Professor Siddiqui mentioned this point. So there are some spectrum of opportunities here also. And again, going back to
So yeah, so actually I want to say, I want to mention one thing that Chinmoy said, because he mentioned that the there all the comes first and all. I want to tell you all that that is not important. It did not come first to do well. So don't focus on those aspects, because if you are studying well, if you are understanding the basics well, you will do well in your life. So those are come first, second, all this stuff, man-made ranking system. So that not always reflect who you are. So do not get disheartened if you are not the first boy or girl in your
yeah,
class. So do not focus on that. I'm sorry, Chinmay, just I have to say that.
no. Thank you very much. I understand. The point I mentioned is just to give an idea that it's not like that the students working in India or working in Indian institute are not the world class. So they are definitely world class. In fact, our Dr. Chattopadhyay is the example, and he's the legend, as we have already told. So going back to a little bit of technical questions again. So related to this talk and as well as in general on the terahertz thing, so there are a couple of queries from someone, Binoy Ayar. How is the on-chip spectrometer sampling the RF? Is it digitizing at the front end, heterodyne or direct RF sampling? So these are connected questions.
Yeah, very good question. I think I saw the question from someone, but I am not able to read all of them, right? So I think
Yeah,
Vinay Iyer, he is at UVS student with Bobby Weichel. Hi Vinay, because Bobby Weichel was my MS thesis advisor.
Yes, Gautam, we met at IMS a few years ago. I don't know if you remember.
Hi. Hi.
Hi, I hope you're
So,
doing well.
and then, Bobby Weichel is the one who actually wrote a recommendation letter for me and suggested for me to come to Caltech. So, of course, Bobby and I go back a long time. Very good question. See, we cannot sample at 500 gigahertz, direct digital sampling at 500 gigahertz, because you know that if you do an IQ sampling at 500 gigahertz, you need to do your sampling at 1 terahertz, and we do not have digital chips that work at that frequency, right? So what we do is we do heterodyning. So our that 500 gigahertz signal, we bring it down to 3 to 6 gigahertz. That band. So right now, we are again to get a 3 gigahertz. If you are doing a 6 gigahertz bandwidth, 3 gigahertz bandwidth, you need to sample at six giga samples. So we have developed a chip that can do 6 to 12 giga samples. And so that's what our IF frequency is, about 3 to 6 gigahertz, so 3 gigahertz bandwidth. And we sample it at 6 giga samples or a little bit above. So it is not direct. We cannot do direct digital sampling of our signal at 500 gigahertz.
right. Thank you very much. There are a couple of queries from Mr. Oyon Kormokar. We know Oyon pretty well because he works at SCL Semiconductor Lab, Chandigarh, which is under Department of Space, Government of India. So Oyon's queries are regarding the of terahertz communication from the space perspective, and the second question is the role of flexible electronics in future space program.
So yeah, these are very broad
Right.
questions, right? You're asking me to predict the future. That generally we don't do. But anyway, I'll give you my opinion. Not really predicting it. So in terms of the flexible electronics is very important, because if you think about it, not only space, for anywhere else, that is flexible interconnect. One of the things is not only the electronic, the interconnects part is very important, because you are putting things together, and then how do you connect them? So if you have a flexible interconnect, and then it is very useful for space application point of view. Also, you have to think about how the properties change with temperature and pressure and all these other environments that you have to be very careful about. So yes, if you can develop flexible electronics, it will be very, very useful. That is for sure. And in terms of the terahertz communication, yes, for terahertz communication is coming, whether you like it or not. High millimeter wave that you see, I am not saying that your next smartphone will be a terahertz smartphone. That is not going to happen anytime soon. There are a lot of challenges. However, back end, that the back hall of your digital that network that you see, communication network, is already moving to very high frequencies, because the data rate that you need to handle is extremely high. And one of the way to go there is to use these high frequencies to get the bandwidth that you need. So it's already coming. And also in terms of point-to-point communication, terahertz already people have shown, for Beijing Olympics, Japan telecommunication, they did from the bird nest stadium to their studio that was actually 5 kilometers away. They did point-to-point communication at, I think, 240 gigahertz range, and
Right.
very high resolution videos. And so you can do terahertz. One problem is this line of sight. As a result, you'll have to think about slightly differently. So massive MIMO that you keep hearing. So those are the kind of techniques that you'll have to use if you are going to use terahertz communication. But again, it provides a lot of advantages in terms of bandwidth, but there is always cons, because the losses, atmospheric losses and others.
Right. Yeah. Thank you. Thank you very much once again, Gautam. As you said that there are challenges, but there are attempts also to mitigate those challenges. So one related question in the same areas is, I mean, I'll also chip in this question after you address. Can terahertz antenna be manufactured in India?
A very good question. You should ask, people who are in India, so they will be able to tell. But my point on that is, yes, I think if you'll have to work with industry, you'll have to work with the capabilities. Is that you have to buy the machines that you need, and you have to buy, that a lot of fabrication, facilities, that with investment, lot of places are investments are being made. One of the places, of course, in Chinmoy's place, ISRO is doing it. IIT Delhi has measurement equipments as well as other facilities. So that, and also IIT Roorkee, they also have people are working in terahertz. So across India, there are a lot of people are working on terahertz. So you should try to actually form a terahertz group in India and interact with each other and see what you can do. See, if we can do something, you can do. So there is nothing magic about any of this. So it is all about available funds, and and researchers. You'll have to push. As a researcher, you'll have to push. Only then it will happen.
Thank you very much, Gautam. In fact, you have been one of our inspiration to start some activities. As I said, I want to chip in on this. In fact, we have designed, fabricated, and successfully characterized some of the photoconductive antennas for terahertz application. So, as Gautam suggested, we need different kind of facilities. So we had a collaboration with SAC, and we did some measurement at ISAT Trivandrum, spectroscopy instrument, and we purchased some silicon lens from Batop, and with this we did some experiment. We are in the track. So definitely there are challenges, but it is possible to do some activities sitting in India also. So let me go to the next question. So this is again is yeah, technical question from Prokhar Gupta. Isn't it possible that the water from the asteroid or meteor and Earth both come from some other source? If we can measure the ratios in the multiple asteroids, then maybe we can confirm. So it is related to the previous question.
So, but let me make a comment here that we find the asteroids actually do not have much water. That is one of the things that we have found. So most of the water bearing carrying are mostly comets, because comets carry huge amount of water, and as they go closer and closer to the sun, and that's when they start giving up their water and gases. So that's what happens. So again, it's very valid question that we'll have to do multiple measurements. So one of the reason I am developing that WhatsApp kind of CubeSat based system is because we can make multiple CubeSats, and then they can get a ride with when there is a main mission going somewhere, and they can, on the way, they can actually throw out these CubeSats, very small CubeSat. Then they can go to a comet and do measurements. So we'll have to do multiple measurements to come to this conclusion. So as I said, we made only about 10 measurements so far. That is not enough. So for a statistically significant number, we need multiple measurements.
Thank you very much, Gautam. We have a few more technical points, but as I said, that some of those are connected and some of those are addressed from a different perspective. Even if you have certain more queries, please feel free to write to us, or you can probably reach Dr. Chattopadhyay directly. He will be very happy to address your queries. But now we want to have a little bit of more interaction, because this is a real opportunity to talk to the leaders and legends through this particular L4 platform. So to begin, I request Dr. Sarkar from IIC Bangalore to say something, because he mentioned that he have some specific queries to you. Dr. Sarkar.
I am audible.
Yes.
Yeah, so first of all, thank you, Dr. Chattopadhyay, for the nice, informative lecture. And well, it is always a pleasure to hear from you. And I believe that I have heard your number of webinars in the last few months during this lockdown online. And particularly in this particular event, it was very inspiring to see some of the glimpses of your journey previously. I think that was not the part for many other webinars. So this particular one was inspiring for us, and I would like to thank the L4 organizers for adding that bit. So, well, question regarding the question, I have mainly a technical one. Actually, I was following your lecture, and there were a number of points. Like one was regarding this CMOS-based synthesizer in the W band and the MEMS in the terahertz. So I was actually intrigued, and because I'm just starting my career, so I would like to seek some advice that if I or someone else wants to work on those particular domain and try to develop them indigenously in India. So what could be the challenges, and how should I approach that actual problem for the design and all? Yeah.
That's a very good question, Devdeep, and good to see you. And congratulations for your new appointment at Ingenuity of Science Bangalore. So Devdeep is very well recognized around the world. So all of you who are students, write to him, ask for a postdoc, ask to become his student. So don't leave him alone. Just keep bombarding him with requests. So that is one. And then, okay, to answer the specific question, if yes, you already have an IISc. I know someone, Gaurav Banerjee. He's a faculty. He is a great researcher, and he does work in CMOS system. So work with him, and first try to solve a specific problem. See what exactly you want to do. Say anything, like let's say you want to build a radar at W band. Why not? Make a big plan. I want to build a radar, and then try to break it down at. You can do a single chip SoC based radar. Most of the radar processing and everything can be done through a single SoC. So then work with Gaurav, and then come up with the design that you need to do and build a chip. Because the fabrication wise, most of the time there are other fabrication facilities. You do not need to build. CMOS fabrication costs billions and hundreds of billions of dollars. So that is not going to happen anytime soon. You can go to TSMC and get fabricated there. So only thing you have to do the design, so that you can do in collaboration with other people, like you have already Vinay and others. Gaurav and Vinay and others at your institute. So that is the way to approach this.
Yeah. Okay. Thanks a lot. And just one more thing I would like to ask, like this is not exactly related to this talk, but a little bit technical. Like nowadays we hear a lot about this quantum technologies and things. So are there any application or things that are going in the space research with this quantum? Just a like crazy question.
Oh yes, answer is yes. Quantum. If you look at quantum computation and quantum other technology, we use quantum technology already. Not in quantum computation. Start quantum limited. Detectors we build. Quantum detector. In heterodyne systems, quantum detected is h nu over k. That is your quantum noise floor, right? That is because comes from the vacuum fluctuations. So we actually build instruments which are almost quantum noise limited. So very close to that the best that you can build using superconducting technology. And in terms of your other quantum technologies, yes, there are a lot of work is going on. And in the when we talk about quantum, we mostly talk about quantum computation. That is because a big thing. But there are a lot of other quantum technology that is currently being used, being developed for space applications. So yes, answer is yes. This is very important area.
Okay, okay. Thanks a lot. Thanks a lot once again for addressing the queries and for this beautiful presentation. Yeah, thanks. Over
Thank
to you,
you.
Dr. Shah. Yeah.
Yeah, thank you, Devdeep. So, one more query for the general audience, including myself. You talked about your early career trajectory, how you have started your childhood and you have reached to the pinnacle of success. Now, as far as the current commitment of yours are concerned, like you are very much involved with your research, you are involved with different administrative activities, you are in IEEE several boards, MTTS, and in general IEEE also. You are a distinguished lecturer, you are associate editors in many journals, I know. So, how do you manage your time to keep your focus, research focus, technical focus, and leadership focus intact? And also, we know that you are very much involved with Indian conferences. Also, you guide and mentor some of the activities. So, this tip would be very, very useful for mid-career people like me and other colleagues.
Oh, that's a very good question. I don't know how to answer that question because, of course, time management is one of the most important aspect of everyone's career. Because how do you manage your time? Because most often when you are busy, you'll realize that if 24 is not enough. 24 hours a day is not enough. But at the same time, I try to actually answer when people write to me, on LinkedIn, on WhatsApp, or an email. I try to answer to all of you, all of them. Sometimes, if I am a little bit delayed in answering, please bear with me, because not that I'm trying to ignore you, but I there are other things to take care of. Yes, actually a very important question because it's not only the broader question as well. How do you balance your personal family life as well as your research career as well as your professional career? So we'll have to actually look into that aspect very carefully. Do not ignore your family. Do not ignore your personal life. Because professional life is important, but personal life is more important. So that is one of the key. And thing is that we'll have to have a team of people working around you, and dedicated people, and you'll have to trust them. In the sense that I never micromanage anything. So whoever wants, and whenever I am working in a group, I give, so this is, give them the broad picture. This is where we want to go, and I do not go and ask them, how much progress you have made. Where are you? Because if you try to do that, then you lose control of everything. Because you do not really have time to do that. So you'll have to trust people to make the right decisions, and then help them, of course, whichever way you can. And this again, do not focus on one aspect of it. Break it out in small chunks and work on all those different areas at different times. But again, every individual manages their time in a different way. So as I mentioned at the beginning, my attention span is not very large. I lose focus very often. So actually, I do something and then go something else. Maybe that's how I'm involved in so many different things and not doing a good job of all of them. So sorry.
Thank you very much. Once again, I think it's very nicely your way of dealing with leadership. Really don't micromanage and you give full freedom to the people you trust on, like myself and Dr. Sarkar. We had some responsibilities in IMARC, and once you gave the responsibility, you fully believed on us, and we just executed finally in the podium. Yeah. Anyway, thank you very much again. So one more, like couple of more queries from my side before some of my volunteers will have some queries to you. like we are IEEE volunteers. We try to involve our students also in IEEE activities. So IEEE definitely bring technicalities in terms of certain access of IEEE journals and all, but that is very generic, and most of the institutions nowadays have their institutional subscription for getting those access. So, at the very early career, what are the benefits that you see, rather foresee, for joining a young students at bachelor's or master's level at IEEE? So, what are the benefits they can harvest in future?
So one of the things I always say, the most advantage, at least from my perspective, is the networking abilities. Because once you become a IEEE volunteer, IEEE member, it actually opens up your networking. You actually are getting access to a lot of people who have gone through, some experience, and this that's very important. Today's days and age, your networking ability, your connection to people is very, very important for your career. And so that is one of the things. And of course, if you become member, you are accessing to this. When you go to an industry, you will find, suppose you are doing an undergraduate and then you just graduate, finish your undergraduate and go to industry, your college might be having access to those journals, those magazines, but the industry, they don't. Then how do you keep connected to this technology world? And if you want to make progress, let's say that you, after undergraduate, for some reason you have to take up job, and then but you have in your mind you want to come back and do your masters and PhD in future, and if you're not getting remain connected to this technology field, it will be very hard. So through that IEEE membership actually provides you that connectivity, during that time, and then you can actually come back and join. So these are the two main things. And also what IEEE does is generates leaders. As you become a member and volunteer your time, you get to interact with people and get trained in leadership, because in your career at some point of time you will be the leader, you will be leading an effort, you'll be leading people. So how to become a good leader, that is very important. In all of us will have to really learn well how to become a good leader, because that leadership takes the institution or all your department wherever you are working in the, whether it's going the right direction or not depends on your leadership. So these are the really lot of important areas that the a membership provides.
Thank you very much, Gautam. In fact, if I remember correctly, many of my academic and professional networking has happened through IEEE platform. In fact, I came to know about Gautam Da, and then many more in different other conferences, the leaders and legends we brought in the last week. So all these happened through IEEE networking. So I think the main point for the students' perspective, as far as the harvesting or the reaping the benefits of joining IEEE, is the networking, collaboration, and also some of the opportunities that IEEE provides to the students and the different conferences, etc. So, with this, I
Sir,
request.
sir,
Yes,
sir,
Professor
1 minute.
Nagarajan. Yeah, please go ahead.
IEEE chair, Chennai is also here. Shanmuganandam.
Yeah, Dr. Samuganathan, good evening. You may ask your question, please.
Good evening, sir. Sir, I'm Shanmuganandam. Actually, see how to get the more funding to do the more activities in the IEEE APS, sir. How to get more funding, because very less funding only nowadays they are allotting for the chapter that societies. So how to get more funding?
Yeah, so it's a very good question. There are many avenues of funding through IEEE. So one of the, as you said, the chapter funding is limited and fixed, because if you are just a single chapter, then you get about $1,000 per year, and then if you are a joint chapter, then you get 500 from each societies. But there are other, there is site. The site is that for humanitarian activity. So IEEE has a lot of different programs. So through that, your chapter can actually ask for funding for those. like if you are organizing a workshop or a conference, as Chinmoy and others they know, then you can actually ask for specific funding from all these IEEE different societies. They have specific programs like education program. They have for meetings and symposium programs. So you can actually approach those individuals. So yes, look into that IEEE. I'm seeing that I have some to that, and do not just depend on the fixed chapter funding. Explore other sources, because IEEE does have a lot of different programs.
Right. I just
Thank you.
want to take this opportunity to add on this, like of both dealing with APS as well as MTTS society, as Dr. Chattopadhyay suggested, there are many other avenues. So you have to conceive and you have to plan your the activities, and then you can approach to the headquarters through proper channel. And if your plan is well, and if you really aim for a good program for the benefits of students, then there is not much of problem in getting those sanctioned. In fact, I know from Goutam that MTT Society has a lot of special initiatives. I believe APS also has those kind of things. For example, during last IMARC, and probably in each IMARC, many students travel and their conference registration fee is completely taken care of by a Microtheory and Techniques Society. So I believe, Shanmuganathan, Dr. Over, you asked, like, APS might have similar kind of activities and avenues. You have to just
So,
see
so my,
those.
my request to my request will be to make a joint chapter. Do MTT chapter as well, not just AP in your area. So then you will have
Right.
more opportunities for funding.
Okay, thank you, sir. Thank you.
Yeah. So I would request, because some of our office bearers of MTTS Kerala wanted to have some interactions with you. So I would request Orijit to raise your point, please.
Good evening, sir.
Please go ahead.
I have one technical question actually. Like in
Please go ahead.
yeah, like in space application, this reliability and redundancy is very important. Like when it goes forward with design, we have to eliminate single point of failure at such things. So now you have shown some CubeSat antenna, CubeSats where they're using some deployable antennas and other such components. In terms of design, how we are ensuring reliability, whether there is any trade-off between the reliability and performance that we have to take care.
So if I repeat the question, your voice was breaking off. So what I understood, you're asking about reliability of when you are having space mission. How do you actually make them reliable, and what are the, and also I saw briefly about someone was asking about reliability as well as performance. How do you actually compromise on those? It's a very good question. Of course, reliability has to be most important, because in space we say that failure is not an option, because if you design something and you send stuff, you cannot go back and fix it if it doesn't work. So it has to be reliable. And how do you do that? You actually through testing. You'll have to do a lot of testing, and that's why whenever there is a space mission, people ask us why it costs so much. It costs so much because you'll have to make it reliable. You'll have to actually look into all this. We call it accelerated life testing. So, okay, the space mission will have certain life. So it should not fail in that lifetime. Then how do you ensure, how do you know that your system is going to work for 5 years? Sometimes it takes 7 years to go to the planet, and then you restart. It has its 3 years of lifetime. Then how we make sure that actually it works? So we do accelerated life testing, in the sense that we elevated temperature. If you actually make a profile of what are the temperature ranges it will go through, and what are the different environment it will go through. So we'll have to actually do those testing in those environment and make sure that nothing is failing. What is the probability of failing? What are the risks? How do you mitigate the risk? Redundancy is not always possible. Of course, if you have a redundant system, then you are mitigating risk by having a redundant system. But redundant system means you need to have twice power, twice the mass. So it's not always a possibility. So you'll have to think through all this, that how do you first assessing the risk, then mitigating the risk, and then coming up with the reliability number, that is, so this is how this reliable is. So that's what we'll have to think about.
Thank you, sir. I have another second question. It's slightly not technical. We already have heard of your phenomenal journey from this, what I can call, from Hooghly to this NASA JPL. So now, in the course of this journey, when and why you chose microwave, and what made you to stick to it?
Okay, that's a good question. Microwaves. So when I was, when a lot of people who are doing undergraduate, you do not really know what you want to do. I had, during my undergraduate, I had a good teacher who was a microwave engineer. So that, kindled some kind of interest. And then I went and joined TIFR. And there I was building a giant meteorological radio telescope that is a microwave frequencies, of course. I started learning more and more and started finding it fascinating. And that's why, but if even if I had not done microwave, it is okay. You want to do microwave. Whatever you do, you have to have the passion for it. And I generated this passion, not necessarily that the day I was born I wanted to do microwave. It is just that I had a good teacher in college, and then got this opportunity to work in microwave area that actually kindled my passion in that area.
Thank you, sir.
Thank you, Orijit. In fact, Orijit, Anu Muhammad and some of our students, they are the real pillar of this chapter behind these activities, the L4 and all the events that have happened. So I want to take this opportunity to keep this in on record, that they are working behind the curtain and behind the scene. They are, the people who are making this chapter successful. Our AP chapter in 2018 got the best chapter award under when I was chairman and Professor Anandan was the previous chair. So I believe our MTTS chapter is also quite vibrant, and all credit to these youngsters and the volunteers. So before we are almost 2 hours, so before we conclude, I just want to have the last question to the speaker, Dr. Goutam Chattopadhyay. You have talked quite a few times that in your group a lot of research happens over the coffee table. So you want to take your colleagues and invite them for coffee. And then one more thing is, that wow, women of wisdom, then women in microwaves, women in antennas. These are different kind of initiatives that IEEE also brings. So I remember in IMARC, you are very particular to have 50% members in some panel discussion and some other kind of stuff. So you always promote the ladies and women in different platforms and technicalities as well. So can you please club these two questions together and bring the perspective which motivate you to have to think that research can happen over coffee table, and we need really the women also in 50% or close to in different IEEE forums and podiums. Yeah.
Thank you so much for bringing this up. Actually, it's a very important question. So, in that respect, I actually, there is a question from Polumi Roy. She's actually a woman. So I saw that. So that I'll answer her question. That will also show that, we really care about women. We want more women to be in this area, in microwaves and all aspects of life. So Polomi's question is that, Enceladus, there could be possibility of life in Europa and Enceladus. And then how those are cold places, how can there be water, liquid water? The answer is that we are finding Enceladus as well as Europa, they have a mantle like our Earth. So there is a source of energy, and that is actually keeping this cold place, the water in liquid form. And that's why we believe there's a possibility of life, because there's a source of energy there. So that is your question, and answering Polomi's question. So answer this, let me first talk about the women, aspect. So if we look around, 50% of population is women. So it is very important that we have more women representation in our, professional life as well. And it is not that there are not qualified women available. It is not true. That we'll have to find them. We'll have to make life more easier for them, because there are a lot of hurdles we put hurdles on their path. So we'll have to go out of our way to make sure that they get this opportunity. they are qualified. They are studying, science. They are studying in, science and engineering. So why shouldn't we, have more women in all this? That's what I always tell Chinmoy. And whenever you are having a panel, make sure that we have women representation as well, because when this is my personal belief that when we have women in decision making process, we make better decisions. That's because all of us are thinking in a different way. So we should not leave out one section of our population who has so much to contribute. So this is very, very important for all of us who are in the position to make a change, make a difference. We should really think about that and make sure that we hire more women, qualified women, and then they are available. Only thing we'll have to, the women has, a lot of, and home scenario, they take care of family more. So in our workplace, we'll have to make sure we make arrangements so that those aspects are looked into. So it is very, very important, and its onus is on us, on men, to make sure that we actually address this. We cannot really tell women, oh, there is not enough women. That is not an answer. I am not ready to take that as an answer. So it is on all of us to make sure that we support all women colleagues. And actually, it's not that they're asking for a handout, they are asking for a legitimate place on the table. And that's what we should support. And in terms of coffee table, yes, I keep saying teamwork, and talk to people of different background, talk to people with diverse background, and I go for coffee every day at when there is no pandemic, of course. And then with my all the colleagues from all different fields, they come, we discuss a lot of things, and that's where we actually sometimes talk about our problems we are facing and how we are trying to solve them. So, and you get different perspective, you get the different inputs, and that's how innovation happens. At the beginning I said, so it is very important, go and talk to your friends, go drink coffee, tea, whatever you would like to drink, and meet people, talk to them after the pandemic is over. Don't go out now. And so that's how you can make innovative ideas come to reality.
Thank you again very much, Gautam. That you have really addressed both the aspects, the research over coffee table, as well as the importance of the women representation in IEEE and different panels very nicely. So before we conclude formally, I would just request two of the student volunteers who work tirelessly along with their academics for these activities of MTTS Kerala chapter to turn on their camera, Akshat, Philip, and Sivada. They work and support on various things, the event flyers and this managing the WebEx platform and etc. Akshat and Sivada. Akshat?
Sir,
Yes, sir. Thank you so much, sir.
Yeah, so
thanks.
Means a
on
lot to
behalf
me.
of all the audience and on behalf of MTTS Kerala chapter, I just wanted to, special applause and appreciation in presence of everyone. Thank you very much for your effort, time, dedication, and the service to the MTTS Kerala chapter. So with this, we have come to the end of this particular program. Once again, thank you very much, our speaker, beloved. I would say our role model also, because for everyone, you need to have someone whom you want to follow, and you have to follow the footsteps. Dr. Chattopadhyay is one such person for me, and I believe for many of you also. The way he has achieved, and he has not still reached the zenith of his career, but still he is a legend in this particular field, and he's a leader also. So with this, we can go ahead with the formal vote of thanks. Special thanks and appreciation on behalf of MTTS Kerala chapter to Goutam Chattopadhyay sir and everyone. So Dr. Anu Muhammad will be proposing the formal vote of thanks on behalf of MTTS Kerala chapter. Anu.
Thank you, sir.
In fact,
On
he's
behalf
doing
of
PhD with Professor Radha. Yeah, go
MTTS
ahead.
Kerala chapter, APMTT chapters, Indian Institute of Space Science Technology, and GEC Barton Hill, we would like to thank Dr. Goutam Chattopadhyay for accepting our invitation and agreed to talk on sensors, antennas, and systems. Sir has covered all aspects during his talk and interactive sessions on space exploration and various requirements associated with their missions, given practical insight, catering all segments like industrial and academic professionals and student community. I would like to thank all attendees, faculties from various universities across the globe, scientists or industrialists working with the various organizations across the universe. I am happy with the enthusiasm shown by the student community who attended the function and would suggest them to involve and join these kind of society chapters and get yourselves technically benefited. I'd also like to thank our college authorities for supporting the and always standing with our APMTT. I would also like to thank the office bearers of APMTT, especially Dr. Saha, Mr. Arjit Mitra, for their extreme support to our college, especially to my undergraduate students by introducing this L4 webinar series, mentoring their projects, etc. Also for your generous support to GEC Barton Hill, which is celebrating its 15 year of SB formation. I would also like to acknowledge the efforts of my students and their tireless commitments, the undergraduate students for our APMDT section. With this concluding, thank you and all to you, Saha sir.
Yeah, so we have one more dedicated public is volunteer over here, Ms. Gopika, who is doing very good research in Indian Institute of Space Science and Technology. So I request Gopika to turn on your camera and say hi to Dr. Chattopadhyay and conclude the session. Gopika?
Hello, sir.
Yeah.
Thank
Could
you,
you
sir,
please
for the
turn on your
nice.
camera? Yeah.
Yeah, hope I am visible and audible.
Yes, yes.
Thank you, sir. Thank you, sir, for the inspiring and informative talk. It's to hear you once again. And it was such a nice session that we actually look forward and we start seeing the dreams. Thank you so much, sir. Thank you so much for taking the time.
Thank you to all of you. I want to thank that for listening in, for tuning in. And I know you will be in India, you'll be hungry by now. It's almost 10 o'clock. So please go and have your dinner. And again, of course, hopefully we'll come out of the COVID on the other side and meet you in person someday. And looking forward to that. And keep up the good work. And again, when you go out, wear a mask. Don't be in good big gatherings. Okay. So, and thank you. Okay. Bye.
Thank you so much, sir. Bye. Goodbye, sir.
Thank you very much, Goutam. And also, I remind all the participants about the fitness tips Dr. Chattopadhyay was having informally before the session started. He walks 8 to 10 kilometers per day. So this is probably another way to combat the COVID pandemic, to keep ourselves fit and agile as Dr. Chattopadhyay. So with this, we conclude the session. Once again, thanking the speaker, Dr. Chattopadhyay, and also for all the audience for their overwhelming response. So thank you very much. We close it formally. Have a good day to Dr. Chattopadhyay and